What happened there? Okay. Um, Radio guys, we ready? Our brains engaged. We're 100% ready to take in some information, Alyssa and Sky. Just waiting on you guys. Okay, exponential functions, guys. Um, Geez, you can tell I wrote this when Marvel was more popular. So we often talk about exponential growth without giving much thought to what it means. For example, Thanos is an exponentially greater threat to the Avengers in Infinity War than Loki was in the first Avengers movie, is something I saw someone say. Um, Using that manner, many people to think that exponential just means big. So in someone's physics draft on the weekend, they said that like the value at 4 volts was exponentially bigger than the value at 2 volts. But that's not really what exponential means. Exponential has to do with how quickly something grows, not just this thing's bigger than that thing. So generally speaking, exponential equations is one that grows that or decays at a rate relative to its current size. Classic example is a colony of rabbits where a single breeding pair can rapidly populate a large area. Does anyone know how rabbits got introduced to Australia? Yeah, some rich guy bought over, I think, 14 rabbits and released them on his property to hunt. Um, he obviously wasn't very good at it. And now they're an endemic pest across Australia. They also are destructive. Well, isn't that unfortunate? And also probably going to kill this recording. Oh, no. Okay. So, you guys know what pyramid schemes are? No? You've done a few yourself? So, a pyramid scheme sounds really, really, really good because someone says, like, okay, if you pay me $50 and I've gotten like 5 people to pay me $50, and then under you get 5 people under you to pay you $50. Now, take away the $50 you paid me, you just made $200. And then each of those 5 people under you, some of their money goes to the person above you. So when you see things like, you guys probably don't come across this, but like once you get a bit older like me, a lot of like middle-aged women on Facebook like sell like, Avon or whatever, or like makeup stuff. And basically they don't really make much money. The only way you make money doing that is to get other people to start selling the product as well, and their money comes up through you because you recruited them, if that makes sense. So the person that started at the top of the pyramid, for everyone under them that is making money, they're making free money. But for the people at the bottom of the pyramid, they're making like no money because a lot of their sales are going to like the people above them in the pyramid. But to the person at the top of the pyramid, they go to like the convention and be like, I'm making $5 million a day with like selling Avon products or whatever. And it sounds really, really good. But there's actually a mathematical reason why it doesn't work for the people at the bottom of the pyramid. Let's have a look at that here. Has anyone like seen that kind of stuff, like the sign up to sell like Nutrilife or whatever, like those kind of things? Yeah. Okay. Layer one, there is 8 people. So let's say I'm the pyramid master. I've recruited 1, 2, 3, 4, 5, 6, 7, 8 people under me to sell this product. Now, they're my original batch, and I'm going to get each of those people to sell to 12 people. Okay, so in the second layer, how many people are going to be in that layer? Wouldn't be plus, it'd be times. 96. So times 12, 96. Now, each of those people has to get 12 people under them. Times by 12 again, what do I get? Uh-huh.
1,000.
What have you done to my calculator, Mia? So what was it, sorry? Okay, so we're 3 layers down, there's over 1,000 people in my pyramid. If I go to the next layer, what have I got?
13,824.
Next layer.
165,800.
So by the time we get to the sixth layer of my pyramid, we are at 1.9 million people. I'm not going to keep writing out the rest of the number at this point. That's not right. 23.8. That should be 23.8 million. Can anyone tell me why is this model of making money unsustainable? Let's imagine we're just doing this I was about to call it a scam. This legitimate financial model in Australia. What's the issue that we're coming up with here? Think about the number 23.8 million people. Sorry? You're on the right track. Australia only has a few more. We're like 30 million maybe people. We're 7 layers into our pyramid, and already the majority of Australia is selling. Who's buying if the 9 out of 10 people are selling for this pyramid scheme? So even if we include overseas, we get like another couple of layers to the pyramid, and then we get the exact same problem where we're going to be in the billions. Who's going to buy our Nutrilife supplements? You will? All of it? Good for you. In terms of what rule could be used to model that, if we think back to our sequences and series, would this be arithmetic or geometric? Geometric. So we could say layer n. By the way, as well, guys, that 23.8 million, that isn't how many people in total. That is the people in that one layer. You'd have to add up all the other layers to it as well. So to find how many people in each layer, it'd just be, the number of people in the layer would just be 8 times 12 to the n minus 1. That'd be people per layer. And then to find the total people in the pyramid, it'd be Sn equals, what's the rule for geometric series? T1 R minus 1. So 12 to the n minus 1 over 12 minus 1. Just for funsies. Can you guys find me how many people would be in this scam by layer 10? So what is S10? S10 equals.
Very, very nice.
By the time you got to the 10th layer of this, there would be 45 billion people in on this pyramid scheme. That is so many people. It's more than like, how many people on Earth? Like 8 or 9 billion or something like that. So it's like almost 10 times. Yeah, no, what am I thinking of? Yeah, I was thinking there's 5 billion. That's embarrassing. Okay. Generally though, if we want to construct an exponential rule, guys, so something where there's massive growth or massive decay, it's continuing at an exponential rate, it's growing really, really quickly, or it's decaying really, really quickly. The rule we use is our function is equal to some number b times ax. Does anyone want to have a guess as to what b might represent in that? Think back to the previous example. Yeah, the initial condition. So b is generally the initial condition.
T1.
You can do either. I generally call it A. But the rules generally say T1. Does anyone want to guess what A is? Yeah. Or your growth or decay rate.
X is number of period.
Yeah. Okay. Let's have a go at solving some problems, guys. We're going to solve it for 1, 3, and 10. The old favorite. Whenever you get exponential growth, we just love talking about algae colonies because there's something in nature that really does follow an exponential model really, really well. So an algae colony measuring 5.2 centimeters squared, so obviously the area on the surface of like a lake or whatever is 5.2 centimeters squared, increases its size by 50% per day. For this, my initial condition, what do you reckon it's going to be? Yep. What about my growth rate? 1.5. I'll put in brackets 150%. How come we don't just use 50? Because if we put a growth rate of 50% in, what that actually means is it's halving each day. But it's keeping the original 100%, it's adding on an extra 50% each day, which is where we get the 1.5 from. So, that means my size based on, what do we want to use for x? D for days. The size of my colony based on days is just 5.2 times 1.5 to the power of d, number of days. Now, we've been asked to solve this for 1, 3, and 10.
So 1 day, 3 days.
Okay. Do we want to solve this 3 times, like put into our calculator 3 times? Well, you can do that. I'm slack, so I'm going to put it into my y equals 2 and then use my table to just get the 3 answers. So, I'm just going to put y1 equals 5.2 times 1.5 to the power of x. Nope. And then table. And in my table, 7.8, S1. Do you understand what I mean by S1, guys? 1 day. 7.8. 7.8 what? Centimeters squared. S3.
17.5 times.
17.55 centimeters squared. And S10. 299.86. 86 centimeters squared. You see how much easier using our table just made that question? I really want you guys to be fluent with going between your rule and your table or your graph, because it makes your life a lot easier. I'm sure as we go through, there's going to be things that you sort of start to realize, like, oh, I could have done it that way in the exam, would have saved me a lot of time, or would have been much easier if I solved it that way in the exam. Our goal is to make it so that you use this as much as possible. Because remember, your brain, while very good at lots and lots of things, calculations are actually the thing that your head is worst at. So getting the calculator to do as much work as possible is what we want to do. The flip side is you need to know what the calculator can and can't do to be able to use it. Questions? Oh, do you guys want to have a crack at B? Is this one going to be growth or decay? Decay. So I'm going to give you guys a minute or two to have a... Oh, no. Left my water bottle downstairs. Oh, it's right there. My day just got way better. I was really thirsty too. I was like, oh, you have to wait for morning food.
You keep that A, which is growth rate decay to 0.3.
Because you're losing 0.3%.
Yeah.
So 0.3% would be... So as a number, that would be 0.003. So your growth rate then, Ryland, because you're losing that much from 1. So it would be 1 minus 0.003, which is 0.997. Be your actual growth rate. Oh. It's delicious. Oh, that's the point. Sky, what did you get for M1? 15239. That does not seem right to me. 6. That seems more reasonable. Can you say that again, please? $438.11. How much money after 3 years, Ryland?
1.52, and then it has E6.
Positive 6 or negative 6?
Yeah.
You get the same 1? I did.
492,723 per year.
Say again?
I got
This one. Yeah. 07962 times 0.997 to the power of x table. 506438. 3 should be 503404.
and 10 should be 492927.
Are you sure about your values in your equation there, Cody? So do you have 0.997 as your... Okay, there we go. Be very careful with those ones, guys, because even a single decimal place off in exponential growth and decay can cause massive differences in your answer because they grow and or decay so quickly. Questions about those ones before we move on? No. You guys are all Gucci?
Or what?
Gucci? Okay. Town in North Queensland is growing at a rate of 8.7% every year due to new job opportunities. Current population is 150,000. A. Create a model that predicts the town's population over time. And B. Calculate how long it takes to reach 250,000 people. I should point out, guys, in this version of the workbook, I have greened the cognitive verbs. So those are the words that tell you how to answer the question. So in this one, when it says create, are you expected to solve that? No, you just need to make the model. So it is a really good habit to, when you see those greened out words, check what it is you're actually supposed to do. If it doesn't say solve or calculate, you don't need to put anything into your calculator. If it says create or sometimes determine or construct, you just need to make a model to go on with. Okay. Let's make our model. Would anyone like to give me some thoughts as to how we're going to proceed with this? Yep. So our initial condition is 150,000. So B equals 150,000. It's not just 8.7 though. What would it be? 1.087. Because it's keeping the original population and it's adding 8.7% on top of that. So that'll be 100% because it's keeping the 100% plus the 8.7%, which is 1 plus 0.087, which is 1.087. So, what letters do we want to use for this function? Sorry? Yeah, it is.
Again.
What letters do we want to use for the population? P for population. What's our variable we're using to model the population against? So Y, or I like to do T for time. So it doesn't really matter what you do, I just like it. So the population over time equals 150,000 times 1.087 to the power of time. Makes sense? You agree with my findings, Tyson?
No. Yeah.
Questions, comments, concerns? Wobbles. Yeah, but we've answered 8 because we have created a model that does what it asks us to. So we ready for B? So for B,
So you just put that in your calculator and find when
that is one way to solve it, yep. So find P of T is equal to, what is it, 250,000. Now, this is where the graphics calculator really shines. There is a way to solve this using logs. Logs is next lesson, so I haven't taught that to you yet, so we're not going to solve it using logs. How would we solve this in the graphics calculator? Yeah, just go to your table and scroll down until you see a number bigger than 250,000. Because if I gave this to, for example, my general maths kids who don't have graphics calculators, the only way they could solve that was guess and checking. So sub in like 10 to the rule, sub in 12 to the rule, and just keep going until they get close. But that's kind of a waste of time. I don't really like questions like that. But you want to go, it'll go over that. So you say, in the year, whatever, year 8, after...
Year 6. Yeah.
It's got some heated debate over this exponential functions question. It's what I love to see. So check in GC table. So I'm going to say y1 is 150,000 times 1.087 to the power of x. So therefore, from table, y1 is greater than 250,000 when x equals 7. Is that true? When x equals 7, it's greater than it. So therefore, the town will pass 250,000 residents after 7 years.
After proposal.
At 7 years, it'll be over it. You could probably say during the 6th year if you really wanted to be a bit more precise, but x equals 7 is when it's over, so after 7 years, we're assuming they check the population once a year, I guess. I don't expect you to say on June the 5th, the population will be. You could technically do it. But you'd have to. You could actually find down to the second, technically, if you really wanted to. You'd have to figure out how many, days in a year. It'll be a whole thing. Okay. Questions? Quibbles? Conundrums? Conniptions. Been a while since someone had a conniption in my class. Generally, I'm the one having conniptions, to be honest. Freaking out, getting mad, having a moment.
Yeah, we have.
Oh, I mean, Sajith is in it, so make up your mind based on that information. Alright, let's have a look at another one. Oh yeah, this question's actually really difficult without logs.
Why would you put it in the law? We do law.
I mean, nah, I like it. It is physics. That's not shocking, Lachlan. We actually might skip this. There is one thing I want to point out, though. One thing I want to point out. In this one, can you see that we have this minus k in the exponential? This is really common in exponentials. And we're going to look at exponentials where it might be something like this. A equals A0 e to the negative kt. So we've used 2 as the base of as our growth rate, essentially. But it's really common to use e as your growth rate, because e is a button on your calculator. Initial condition, basically. It's another way of saying initial condition. Amount at time 0 is what it sort of means. E is called the natural log. It's similar to pi. It's a non-terminating, non-recurring number. It matches really well with exponential growth. So because it's easy to use and it makes logs easier. So we often use base E. But if we're using the growth rate of E, we need to modify our power instead. So if we want it to double every 5 years, E won't necessarily do that. So we put this K term into the exponent, because it then lets us control how quickly the equation grows or decays. So we will see more of that in a bit. Not today, though. But I just wanted to let you know why that's there. And I'll get you to have a go at question 2, 3, and 4 on page 435.